All right. Well, happy week 10. Week 10 Monday. It's June. Just I guess that's it. So, I guess well, I still have to figure out writing your final exam. But that's coming up, right? So that will be on 1 week from today will be your final exam. And I'll talk more about it on Wednesday, but it will be remote, so you can take it at home. It'll be during the designated time. So I'm gonna ask everybody to I don't know, log in on Zoom or something, and then you'll have kind of this 3 hour window to complete the final exam. But it'll be like a homework thing. I'll post a Jupyter notebook, maybe some data files, and then I'll ask you questions. And right now I'm thinking two parts. One will be like a data set, and you use like pandas and matplotlib to do some basic data exploration, exploratory data analysis. Okay, things like grouping your variables and finding summaries, and maybe there'll be two tables that you have to kind of join together or something. And then the other part will be I'll probably give you like a class definition, or I'll tell you to define a class, and then you'll have to like add some methods and whatnot to this class. And so you should be familiar with some basic Python functions and writing. So that's kind of the idea. It's take home. I mean, you'll do it at home, and you got the 3 hour. So it will be. I don't like. It's hard for me to tell you like don't do anything. So like you can obviously look up documentation and things. I don't know. I don't know how much internet I want you guys to use, but I don't know if there's much I can do to like restrict it either, to like actually enforce anything. So I'll think about this, but it might just end up being like, other than like talking to a friend, it'll be open resources there. Okay. Okay. Yeah, I know, right? Like, you just throw your entire final exam into ChatGPT and see what it says. I don't know if that's a good strategy, but who knows? I don't know what the future of computer programming is going to look like. Okay, let's see. We have okay. This is week 10, and I was gonna make I'm not gonna. I hope this doesn't backfire. I'm not gonna put on lecture view quizzes, okay? But I'll still lecture. I'll be here, and I will put up content that I think is interesting and or relevant. So today I'll just do very, very, very basics of modeling in Python and introduce kind of our two prime, I guess, packages, stats models and sklearn in Python. And these are some of the packages we have. And then, we'll see what else I get to this week. Okay, so let's do that. So yeah, no view quizzes, but I don't know. I hope you still come to class. All right. So what did I write? I wrote the most popular package for modeling data in Python is scikit-learn. Okay. But scikit-learn is very much a machine learning package. It's not really suited for your traditional stats stuff. If you want traditional stats stuff, honestly, R is probably your the tool of choice. But if you want to do it in Python, then Python has stats models. But yeah, I would say, well, our department loves R, and if you are going for traditional stats like ANOVA and linear regression, which are still really useful tools, I would say R is probably the way to go. All of the diagnostic stuff that you have in R that's available to you is it's hard to beat. Okay, and then for machine learning, then Python is probably better at machine learning than R. I don't know. I don't think I'll get in trouble for saying that. but yeah, as far as machine learning stuff, probably Python, you're going to get faster performance, and then kind of the community, machine learning community is, I would say, more bent on using Python for all of that stuff. But yeah, I'll show you, like, if you wanted to use stats models and do some traditional stats stuff, we'll do that. Okay, so you might have to do Conda install stats models or pip install stats models to do this. In general, if you're using Conda, you should try to install everything via Conda rather than doing a mix of Conda and pip. But you have that. Okay, so and then what's the difference between Conda and pip is Conda can install stuff outside of the Python world, whereas pip is very much just Python. So okay, so anyway, load up NumPy, load up Pandas, load up Matplotlib, we'll load up Seaborn. And then as far as stats models goes, there are two ways to interact with it. You've got the stats models API and then the stats models formula API. Stats models formula API is loosely akin to R's formula notation, where you do like y tilde x and things like that. And then the stats models API is modeled a little bit probably towards like scikit-learn, where you have a vector y and then a matrix x, and then you say, predict y based on your matrix x. Okay, I am going to create just a very, very, very tiny data set. Okay, your points are 1, 2, 3, 4 for x. Y is 2, 6, 4, 8. Okay, and so this is the plot here, 4 data points, and you can fit a linear regression model. Did you guys ever learn how to calculate correlation by hand? Okay. So anyway, this is a thing where if you calculate the correlation for these 4 data points, you get a correlation of 0.8. But then when you do the t-test for significant correlation, even though it's 0.8, you get a p-value of 0.2, indicating it's not significant. And that's because you only have 4 data points. So, but anyway, this is what you have. And then we could say, all right, fit, here's this, and we can ask Seaborn to do a linear regression thing, and it does this. With Seaborn, even though it fits a line, it will not tell you what is the slope and intercept of this line. That's like Seaborn's philosophy. It's like, I can do it, but I'm not going to tell you, right? Okay, so all right, stats models formula API. It's very much kind of like R, all right? And you just do like y tilde x, data comes from this data frame D, right? So I've joined the data frame into this. Here's our data frame. I got a column of x and a column y, and so I can do that. Now, when you create this, it's a little bit weird. It just creates this model object, and kind of going along with Python's lazy design is that it's not going to calculate what your coefficients are until you ask it to fit the model to the data. So it feels a little bit strange because in R you just say, hey, LM, and then it fits it and it calculates all of this stuff. Python says, okay, I'll set up the model object, and then I'm not going to estimate the coefficients. And so you have to call, once you create your model object, you call model.fit, and then you get your results. This is, you get a regression linear model results wrapper object. And then and here you can do this. What did I hear? The intercept here is artificially too big because what was wrong? Oh, okay. You know, I think this is coming from, I don't know where these comments came from. Somewhere else. Okay. But anyway, here is, this is the results. Okay. So you have intercept is 1, coefficient is 1.6. Okay. And then you get standard error, you get test statistic t, you also get a p-value associated with x, and again, this is going to be the same as your correlation. When you have simple linear regression and you do a test for significant correlation, it's the same as, you're going to get the same p-value there as you would for, I guess, the coefficient on your slope. Whatever. Okay, so anyway, you get a p-value of 0.2 here and whatnot. It also throws in all of these other things like your AIC and your BIC and what else? Number of observations, degrees of freedoms for the residual, degrees of freedoms of the model. So 1 extra degree of freedom for basically the slope term. You get an r-squared, adjusted r-squared, et cetera, et cetera, et cetera. So all of these things that maybe we've learned about. I don't know what these things are. Durbin-Watson and Jarque-Bera. I don't know what that is. What is that? Do we learn that? Jarque-Bera test is a goodness of fit test of whether sample data have skewness and kurtosis, matching a normal distribution. Huh, okay. It's always not, okay, well, I didn't learn it, so, but it's there. Okay. All right, we can also create a plot. So once you have your model results, you can do stats models graphics, AB line plot, model results equals results, and then you can add the scatter plot to kind of get that. So if you just do the AB line plot, you just get the straight line, and then if you want to add the data points, you get that. You can set your x and y limits, and then you can show your plot. Okay, so that's, I don't know. This is what you have. Okay, and then if you want the corresponding ANOVA table, which is not super interesting for linear regression, but there it is. You know, your source of variation degrees. You get 1 degree of freedom associated with x, and how much does it account for? It does this. You get that. Okay, and then if you want to make predictions using your model, okay, you can do results.predict. And you plug in whatever number you want to plug in, okay? So you can do results predict. Here I give it a dictionary of basically the value x, and then I say, hey, make a prediction for 2, and I get 4.2. I believe I can also do array, and I think I can do, you can plug in multiple values with an array and get predictions for each of those things as well. Okay, so that's your stats models formula API, and then you can also do linear regression or whatever using the NumPy array notation. Here, where is the documentation? So we should let's open up our documentation here. Stats models. Okay. Well. Okay. So here I have x. X is just a vector 1, 2, 3, 4. If we want to create a linear model using array notation, we basically have to make a big matrix X, And in this case, we need a column of ones for the intercept, and then a column for our x variable, and then you can add whatever you have. And then so an array notation, basically your predicted y's are just your you have your matrix of beta coefficients times x, right, where beta is going to be your intercept and slope term. And so here you need an array for your y values, okay? And then x has to be a matrix, okay? It doesn't like it if x is just an array. So you say create a ordinary least squares model, y comma x, and then with the fit, you do dot fit, model dot fit, and then you can get your results, and you get the same kind of thing, right? The capitalization is different. So when it's if it's not the formula, so if it's regular, the Stats Models API, you use all caps OLS. For weighted least squares, you have all caps WLS, and then generalized least squares is GLS and things like that. And then when you use the statsmodels.formula API, okay, then everything's all lowercase. Okay, so this is how, I guess, Stats Models clues to you that you're dealing with the formula API or the general API, which uses matrix notation. So the formula API, you've got lowercase OLS, lowercase WLS, lowercase GLS, pretty much the same models, but yeah, you've got kind of the capitalized versions and things like that. A lot of these things are actually, I'm not super, oh, okay, and then generalized linear models, GLMs, you've got that, and then these other models, actually, I don't even know how to use these. Poisson zero inflated model. I don't know. Oh yeah, and then you gotta love it, right? I'm used to calling everything your response variable and your predictor variable or input, things like that. And I forgot there's another pair of words you can use, the endogenous and exogenous variables, which who calls it that, right? A one-dimensional endogenous response variable. The dependent variable. See, these are like, this is my least favorite. I hate the term dependent variable because that implies the independent variable is like not related to but by definition dependent, like, anyway, exogenous variable. So does anybody else use endogenous, exogenous variables? Maybe. It's like a thermodynamics term, right? I don't know. Okay. Or is that, I don't know.
Endothermic and exothermic.
What is endogenous? Having an internal cause or origin contrasted with exogenous. Oh, I guess it's because of biology. Is this like Stats Models has a bio stats background? Whatever. Okay. All right. So anyway, OLS y comma x, you fit, you get the summary. The summary is exactly the same because it's the exact same data. And then you can say, hey, give me this. And then just to show you that you could also have you can also do linear algebra, right? So x transpose x inverse. So you can do NumPy linear algebra dot inverse to invert a matrix. So that's x transpose x. The @ sign is the matrix multiplication operator. X transpose x inverse multiplied by x transpose y, and you get the same intercept and slope, 1 and 1.6. Okay, all right. Here I'm gonna just make up some data here, and this is I'm just copied this Stats Models notebook directly. So we're going to just generate some random data between 0 and 10, and then we're going to add a column between x and x squared. So you can kind of see this column is 0.1, 0.2, 0.3, 0.4, 0.5, and then the next column is that column squared. So 0.1 squared is 0.01, 0.2 squared is 0.04, and so on and so forth. And then if you look at the last view, you have 9.5, 9.6 up to 10, and that gives us 90.25 up to 100. So those are my two columns. And then what we'll do is we will generate some random normal epsilon values. Okay, so this will be just random noise, and then there is a function where you can just take an existing X matrix and you can just do add underscore constant, and that will just add a column for 1. Okay, so I can do that. And let me just show you what X looks like. So now X has a column of 1s, and then 0.1, 0.2, 0.3, and then 0.01, and so on and so forth. And then so my Y values is I'm going to do basically X times beta. So it's going to be the intercept is 10, the slope for X is going to be 5, and then the I guess the coefficient for X squared is going to be 2. And so those will be the true values, and then we're going to just add some random noise to the true values. Okay, that I generated here using the random variables. Okay, so I can just kind of say like, hey, let's look at the first few columns, and then the true values, and you can see we have 10, and then 0.5 times x1, and then 5 times 0.1 and 2 times x squared. So that's going to give me 10.52. And then if I do this, 5 times 0.2 is 1, and then 2 times 0.04 gives me, so I get 11.08. So these are the true values. And then we can see what the actual values are because we've added random noise. And the random noise has a what do you call it? Standard deviation of 20. So it's like plus or minus quite a bit. But let's fit our ordinary least squares regression model. So we're going to just take Y and X, stats models OLS, model.fit, and then let's print the summary. Okay, so there we go. Its estimate of the coefficient is 16.8, so quite a bit off from the actual value of 10, but within one standard error, or within a little bit more than one standard error. And if we look at our 95% confidence interval, the true value of 10 is somewhere in there. The coefficient for x1, the actual value was 5, and it estimated 2.1. Okay, so we feel like, oh, this is not doing a good job. But again, the 95% confidence interval, it's got quite a bit of standard error, so it's still in there. Okay, and then as far as the x squared value, it got 2.2. The true value is 2, and it got that one a little bit better. 95% confidence intervals, kind of all over the place there. But all of these are, we're getting a significant term for the intercept and the x squared coefficient, not one for the linear coefficient, although the linear coefficient does play a significant role in there. Okay, so these are our parameter estimates. We get it in the summary table, but you can also just ask for results.parameters. You can also ask for your R-squared results. So within the kind of stats models results, there's all kinds of different attributes that you can kind of get out. You can ask for directory DIR results for all of the different things you can ask for, which is quite a bit. Basically, they are formatted nicely in this table, but if you wanted, like, I want the p-values out of here or something, you can ask for results dot what is it, p values. Okay, and you get the same numbers, 7.7 times 10 to the minus 3, which I think is what we have here. Okay, rounded up, 0.008, yeah, but that's 7.7 times 10 to the minus 3. So, you know, basically everything in that summary table is accessible in the results structure. Okay, all right, you can ask for get all of the predictions, all right, and so you have this thing called summary frame for the prediction, which is basically it will say, all right, this is my prediction for the first observation, remember, which was at 0, and so that's just going to be the coefficient here, 16.85, and then you get a confidence interval lower and upper, which reflects what we have here, and then you also get a prediction confidence interval, right? So we know the difference between confidence interval for the mean versus the prediction interval, which is always wider. So one is the confidence interval, because if you have your true relationship, one is the confidence interval for the true value that is supposed to be the true relationship between x and y, and then the other one, the prediction interval, is when you make an actual value comes into the future, like I'm 95% confident that the actual value is going to be between some range, which is not necessarily the mean. And so that range is much, much, much wider, okay? All right, so anyway, we can plot all of this, okay? So here I can take the prediction interval, which will just be the observation confidence interval lower and observation confidence interval upper, okay? And so here we're going to create a plot with the actual data and then the true value along with the fitted line. And then, okay, so what are these things? So remember Matplotlib's funny formatting? Okay, R is going to be a red line. Dash dash means I want a dashed red line to draw this thing. And then R dot dot is going to, or R colon is going to be I want a dotted line for all of this, right? So this is kind of our shortcut here. So, so this is what we have. So the true relationship is shown in blue, and then our predicted OLS fitted line is this dashed line in red. And when you look at it like this, you're like, oh, that's not so bad, okay? Because when you look at the coefficients, it feels like, because the true values were 10, 5, and 2, and we feel like, oh, 16 and 2.16 and 2.2, that's not really great. But then when you plot it on here, you're like, oh, that's not so bad, okay? And because there was like so much noise, right? We had the standard deviation on the error was quite a bit, so we have all of this. And then they're always having a party every day. And then we have a dotted line. This is the prediction interval, and we see, oh yeah, you know what? The prediction interval actually does a good job of kind of getting most of the actual observations within there. Okay, so anyway, that's stats models, okay? So I wonder what class that is.
We can check.
Huh?
We can check.
Jams. All right, next time I'm gonna have Python music, something. There's got to be a fun. I'm jealous. Okay. All right. So that's stats models. All right. We'll keep going, and now I'll just introduce scikit-learn. So all of these things. Look up scikit-learn. All right. Scikit-learn is spelled this way. Machine learning in Python. And okay. So one thing that is so great about scikit-learn, it has like some of the best documentation out there. And so like you could approach a topic that you know very little about, And then they have not just like how to do it in scikit-learn, but also like a full explanation of like some of the concepts and stuff, because that's like machine learning is this double-edged sword of like, hey, we can fit some really cool stuff, but I have no idea what I'm doing. And so the designers of scikit-learn have taken the time to write some pretty good documentation here. So let's do like, what are we going to do? Our first one, we'll do k-nearest neighbors. So let's look. Okay, so we'll click nearest neighbors, and we want nearest neighbors classification. Okay, and so you can read about the nearest neighbors classifier, and this is kind of like stuff that we have, and we'll click the k-neighbors classifier, and then they also have an example. And so here is, you can kind of read through this, and it's pretty good. This fully kind of documents how the k-neighbors classifier works here. Okay, so what we are going to do is we will load up our favorite Iris data set from sklearn. Have I done Iris dataset in this class? I don't remember. I feel like we've used, yes, no, maybe? All right, Iris dataset, it shows up everywhere. Okay, so we'll call up load Iris. The internal data sets in sklearn are stored as what's called a bunch. And a bunch is basically a dictionary, except like some of the objects are like data frames, okay? So if you ask what are the keys in this bunch, you have the data, the target. So the data is going to be your X matrix, and then the target will be your Y vector. And then you have feature names and stuff like that. So if you do this, here's your X matrix. So this would be, sepal length, sepal width, petal width in there. So, oh yeah, I guess iris.feature names, sepal length, sepal width, petal width. And then our target, we have, Setosa, Virginica, versicolor, and the target names. Setosa, what did I say? Versicolor, Virginica. Okay, so those are the 0, 1, 2. And then you got a description of the Iris data set. 150 instances, 50 in each of the 3 classes. These are the summary values, and from R.A. Fisher, and so on and so forth. And it gives you our nice little annual eugenics. Yeah, that's the reality is, as much as we are grateful to R.A. Fisher for his contributions to statistics, is he was a eugenicist, and so he was into like measuring things out and saying like, this is what the ideal genetic sequence would be, or something. I don't know, but anyway, so that is what we have. Okay, the use of multiple measurements in taxonomic problems. I don't know, does this journal even still exist? I'm a little bit afraid to look it up. Okay. All right, so anyway, let's we'll do a train test split. Okay, so train test split is going to split your data into your training and your testing thing, and so we'll do 20% into our test size. Okay, and then so out of 150 observations, 20 observations are going to go into our test set. You can also specify a stratifying variable. Am I getting ahead of myself? Maybe. Because I haven't really explained cross-validation at all to Stats 21. But so the idea here is, if you want to evaluate how well your models are doing in machine learning, is you want to kind of have a test data set, which is like data that wasn't used to estimate your coefficients and things like that. And if you only have like 150 observations total, you have to kind of artificially induce this. So you take your 150 observations and you set maybe a fifth to a quarter, maybe even a half or whatever. But we're going to just set aside 20% of our data, and we'll like hide this away, and we'll say, hey, make predictions based on these 120 observations, and based on that, try to predict these things that you've never seen before. And if you're able to kind of predict these things that we've never seen before and do a good job, then we feel like we've done a good job. Versus like, if I show you everything and then you're able to predict everything perfectly, is it like, did you actually learn the pattern, or are you just memorizing things, right? And so we do this kind of train test split. So when we look at our training data, we see we've got 120 observations rather than 150. And then we can see how many bin count, we'll see like how many of each. And so just to kind of make sure we're going to predict things well, we're going to have 10 Setosa cases, 10 versicolor, and 10 virginica things. Okay, so actually I don't need this anymore, but we'll, so this is what our data look like. I've joined up the species into our things. I don't think there's any infinities, but it's good practice to just get rid of your infinities and replace them with missings. Otherwise, that's going to like blow up your predictions. And then we'll do a pair plot. And I don't know why I'm getting all of these warnings here. I hate it. But it says future warning, use infinity as NA option is deprecated and will be removed in a future version. But I don't have any infinities. I just removed everything. Okay, but anyway, this is what our thing looks like. We have our 3 species, and right now they're just labeled 0, 1, 2 instead of Setosa, versicolor, virginica. But we can see like, okay, definitely you can kind of cluster your data into different things. Okay, we're going to do a k-neighbors classifier. Arbitrarily, I'm going to use 5 nearest neighbors. And so right now I have a k-neighbors classifier object. We're going to fit the data to our training data. So we say fit between our x train and our y train, knn.fit. And it says, okay, I did that. And then now we'll make predictions on our test cases, okay? And so it says, here are your test cases, and I predict 2, 0, 1, 0, 0, 0, whatever, okay? These are the actual values. And then so now we ask, okay, did it get any of these wrong? And we can compare them one by one. And I think it got this one wrong. All right, but that doesn't really mean a whole lot. So you have a few tools. One is we have something called a confusion matrix. A confusion matrix is something we use in classification things where we know the true answers and we have what we're predicting. So if we know the true answer is class 0, Setosa, okay, versus what did we predict, okay, we got it right 10 out of 10 times, okay? So the true answer is in the rows. So this row represents when the true answer is class 0. And it said, hey, when the true answer was class 0, it got class 0 10 times. And it predicted class 1 0 times, and it predicted class 2 0 times. Okay. We see the one error. So what you want is all of your values on the diagonals, or at least you want in a clustering problem. This is a classifying problem. So in a classifier, you want everything in the diagonals. In a clustering problem, if you actually know the actual structure, you want being in the diagonal is not as important, but you want everything concentrated in one value in a row. So anyway, what we have here is when the true answer was class 2, that's this row 2 here, it predicted class 0 0 times, but it predicted class 1 1 time, and it predicted class 2 9 times. So here we have 1 error out of 10 for class 2. So in total, our accuracy would be, we got it right 29 times out of 30. And so we have that, okay? if I did a 1 nearest neighbor rather than a 5 nearest neighbor? So here's my k-neighbors classifier, 1 nearest neighbor. We get the same performance, okay? I could try using the 25 nearest neighbors, which is not a good model. But you know, as far as performance goes, it only has, it's slightly worse with 2 errors, okay? 2 errors instead of 1. So we have that. Okay, how many neighbors should we use? Should we use 1 neighbor, 5 neighbors, 25 neighbors? Okay, we could use something called grid search. And what this will do is it will fit the same machine learning model a whole bunch of times, but change up, you know, these hyperparameters of like, do I want to use 1 neighbor, 2 neighbors, 3 neighbors, 4 neighbors, or whatever. And so, so here I'm going to create a parameter grid for it to try out, and we're going to say go anywhere from 1 to 50 nearest neighbors. Okay. And then another thing you can use as far as your k-nearest neighbors, your k-neighbors classifier, another option is this weights parameter, okay? So in the k-neighbors classifier, the way a k-neighbors classifier works is, let's say you have this thing and you measure like the 5 nearest neighbors, okay? And we say, okay, these are our 5 nearest neighbors, and let's say this was class A, class A, class B, and class B, all right? So in this case, we have 3 Bs and 2 As, and so our prediction for this observation would be B, okay? And that's how the traditional k-neighbors classifier works, is you say, these are my k nearest neighbors, in this case, my 5 nearest neighbors. Out of my 5 nearest neighbors, 3 of them are B, 2 are A, so 3 to 2, B wins, okay? You can do something called a weighted k-nearest neighbors, and basically it's going to measure the distances. So, you know, maybe a better example is, here's my prediction, and then I got these points, and something like that, okay? So these are my 1, 2, 3, 4, 5 nearest neighbors, and these might be A, and these 3 are B, okay? So with my 5 nearest neighbors, the 2 closest ones are A's, but I have like 3 B's, okay? And a weighted k-neighbors classifier will give heavier weights, and will say these 2, even though there's only 2 A's and 3 B's, the A's, their votes count more because they're closer. And so that would be a weighted neighbors classifier. And sometimes it might work better that way. I don't know, okay? So we're going to say, hey, try out going anywhere from using 1, 2, 3, 4, 5, up to 50 nearest neighbors. And try using uniform weights or distance-based weights, okay? And so that's like 100 models to try out. But Grid Search CV is going to automatically do all of this kind of very quickly for us, okay? We're going to do it with a 5-fold cross-validation, which just says basically take 1/5 of your data, set it aside, predict on the other 80%. So use these 80% to kind of try to make predictions for this remaining 20%, and evaluate it, and then repeat it 5 different times, and just see what your overall performance is, okay? So manually, this would be a huge pain in the butt to do, because you'd have like 100 of these things to do, and you got to fit it 5 times each to get a full performance. But scikit-learn kind of automates all of this, and so we just let it run, and it's done, okay? Oh, no, it hasn't run. Sorry, we just set it up, and then now we run it, okay? So we do knncv.fit, and it says it's doing this, and we can ask for what's the best performing model. Apparently 13 nearest neighbors, and how well did it perform? Apparently it got it right 98% of the time, which I guess is fine. You know, it was correct 118 out of 120 times. This is its confusion matrix. On the test set, it got it. We get 29 out of 30. So it's not that much more impressive than than the other models, but you know, that's the IRIS data set too. So okay, and then individually you can see this is how it performed on the different 5 cross validations. And so it got a 100% correct 3 out of the 5 times, and then on 2 out of the 5 times it got one of them wrong, which is fine, but that's how that goes. As far as other classifiers go, so you can go to classification and you can see you know, some of the different classifiers you have. We can also do like a naive Bayes classifier, okay? Which, you know, again, as far as this class goes, Stats 21, I haven't really talked about any of these things. And so I don't know how familiar you are with them, but the Gaussian naive Bayes classifier, how much can I say about this? You know, you're fitting a normal model to numeric variables, okay? And the naive Bayes is that we're just assuming all of our numeric variables are uncorrelated, which is not going to be a great assumption, but it certainly simplifies the mathematical calculations. And so basically, it's going to be something like, you know, when we look at this data here, okay, I don't know, a variable 2 is, I think, petal length, okay? And we can see, you know, Setosa has short petal length, centered around 1.5, okay? Versicolor has petal length, I don't know, 4.5 average, looking at this, and then Virginica has petal length 6 on average or something, okay? And so basically when a new observation comes in and it has a petal length of, say, 3.8, we're going to say, well, you know, that's closest in the versicolor territory. So it gets the highest probability there, okay? You know, it gets a little bit trickier if you get something like 5.1, where it's something in between versicolor or Virginica, and then it says, okay, well, you know, maybe something like that. But anyway, the naive Bayes just says, all right, let's just kind of look at these things numerically, and which one did it kind of closest to? That's going to be the one with the highest probabilities. And so, you know, we fit it to our data, we make it predictions, we see how well did it do. Basically, it's doing pretty good. It keeps making one mistake, and it's probably the same. It's like, let's see here. What's the one observation that keeps throwing us off? It's probably this one dot, right? One of these dots where it's like, I don't know, this one right here maybe. It's like one of these is looks a little bit too much like the other one. And maybe they made a mistake in recording the data. I don't know. But who knows? This is what we have, and we're grateful to the IRIS data set. Okay, we'll wrap things up here. We'll see what other topics I pick for week 10 that are kind of fun and interesting in Python. But we'll see you then. All right. Have a great rest of your day.